Hi. So having investigated, maybe before we talk about the Bernoulli constant, I would point out a couple of features of this solution. You see, the point is the sphere disturbs the flow in its vicinity around here, say. That's because so this is evident from the fact that the streamlines are slightly distorted due to this presence of the sphere. Far away, it's undisturbed. And if you look at the solution, it looks just like that. If you look at the solution, this is the solution far away. This is what dominates far away, and this is what dominates close in. And there are some funny features to this solution, right? At r equals 0, there are some funny features that essentially what I'm trying to say here is that this is an exterior solution. This is a solution that's valid for the exterior of the sphere. So the boundary conditions we applied are valid on the surface of the sphere and far away from the surfaces of the sphere. We are not saying anything about the interior of the sphere. If you want to consider that too, there are some other things called doublets, which we don't have to bother with at the moment in the interest of moving on, right? So moving on, I won't bother too much about this. Let's talk about something that's called the Bernoulli constant. You might have heard about this, and the reason I'm bringing this up is because in some ways this is our first encounter with the energy equation. Okay, in some ways this is an energy equation, so to speak, and it also utilizes the concept of a streamline, something that we've been talking about quite a bit. And you can also derive some fairly nifty results that have to do with physical applications using the concept of a Bernoulli constant. Right? So let's plunge right ahead. Let's start with the Euler equation, which, if you remember, the Euler equation is the momentum equation for fluids that are inviscid, right? Momentum equation for inviscid fluids. So we're sticking to situations where the fluid where viscosity is neglected, right? So the Euler equation is something that we spend some time on, so we're familiar with, and just to emphasize, this is the Euler equation written down in the Eulerian frame. In other words, the frame of the lab observer, right? So that's the Euler equation written down in the frame of the lab observer. The left is ma and the right is F. Two different kinds of F's. These are body forces, these are pressure forces, right? So let's move ahead. Let us now characterize a body force using a potential. If it's a gravitational potential, then it's easy enough to write. There's a reason, right? So and you can already see from mathematically, if you write this down as a gradient of a potential, this is a gradient of a scalar pressure and this is the gradient of another scalar field, so you can absorb both the gradients. So there's a reason. Also there's a physical reason. Acceleration due to gravity, it can indeed be written down in terms of a gravitational potential. So there's the utility, and you recognize that this term from vector algebra can be written down like so. This really follows from the definition of this. You would have seen this kind of a thing as an expansion of this quantity. This is equal to, you take this to the left, this is equal to 1/2 minus this is the form of the identity that you might be a little more familiar with, and mind you, this u dot del is not the same as del dot u. U dot del is the directional derivative, ux d over dx plus uy d over dy and so on and so forth. Okay. So, you just rearrange this and it's simply a way of reformulating this one, and there's a reason. One of the reasons I can already point out is you see this u dot u, it's like u squared. Yeah. So, half u squared is like the kinetic energy per unit mass, right, and this we can get rid of. So, bear with me for a minute and let's go ahead. Right. So, and now we say for steady flows, we emphasize the word steady flows. So, steady flows are ones where the time derivative is 0. The time derivative as discerned by the lab observer, as discerned by the Eulerian observers. Therefore, this entire term vanishes. We don't have to worry about this. Vanishes. For steady flows. So, we don't have to worry about this term at all. We only worry about this, this and this. And in addition, we take this to be the gradient of a scalar potential. Right. Now, so throw that away and all we are left with is this, where we have made use of this result. Right. Now, let us integrate this entire equation along a streamlined element dl. So, you are not following, you are not going along x or along y, you are going along a streamline. Okay, you are integrating along a streamline, very important to keep in mind. Okay. Now, dl by definition, dl the length coordinate is along a streamline. In other words, is along u. That is a definition of a streamline, right? The streamline is a line that points along u, right? Therefore, dl is always perpendicular to u cross curl of u. Why is that? Well, whatever this is, curl of u, whatever direction it points in, you are crossing it with u, right? So, this entire thing is always perpendicular to u. In other words, is always perpendicular to dl. Yeah. First of all, I mean, apart from this, this thing is simply integrating. This is simply this. Okay. So, this line is simply expressed here. Okay. And then we make use of this one. So, dl is always perpendicular to this entire thing. Yeah. So, the dot product vanishes. Right. So, we can throw once you integrate, you can throw this the integration of this entire middle term away, gone, because of this property, and that yields, you see, dl dot gradient of half u squared. So, this is a perfect differential, right? So, you simply get half u squared, very simple. Okay. And this is also kind of a perfect differential. So, it is really dp over rho and you are integrating over dp. Sometimes many people get a little careless and just write this as p over rho. Okay. This again is a perfect differential. So, you simply write phi when you integrate along the streamline. It is a perfect differential. So, this is a central result, okay, and because it is a constant. So, this is what is called, many times people write this as the, you guessed it, it is the Bernoulli constant. The Bernoulli constant. Okay. This is essentially a statement of energy conservation. If this is not immediately evident to you, you can see, half u squared is kinetic energy per unit mass. So, the rest of them had better have units of energy, and you can check that. This is the gravitational potential has the units of energy, and this also, if you put down the units properly, you will find that it has the units of energy per unit mass. Okay. So this is essentially a statement of energy conservation along a streamline. No surprise, right? Since we integrated force along a line element, what we did, you recall, we started from the Euler equation, right? Euler equation, this is ma and this is f, right? So we essentially integrated f, we essentially did, we essentially did f dot, this is what we did, and this is exactly how you get work, right? This is, you integrate force along distance, you get work, and that's it. So it's no surprise that we get energy, okay, that we get a quantity with the units of energy, the energy per unit mass to be precise. But the remarkable thing about this is that the energy, it turns out to be a constant, and this is called the Bernoulli constant. Okay, this is yet another label for a streamline. The stream function was one, and this is another very important label from a practical point of view. This is yet another label for a streamline. Okay, right. So here's an application of the Bernoulli constant. The application is that of flow from an orifice. So what you have is a container of water with an orifice here, and you must have encountered this many times. Perhaps specifically from the point of view of a Bernoulli constant, you must have encountered this problem several times. And you have and the entire container is subjected to atmospheric pressure, and and you have water receding from the top under the influence of gravity pressure, and you have water flowing out from here like so. The question is, what's the speed at which water flows, and the height of this is h right here. This is h. Okay, so turns out that you can solve this problem quite simply. The assumption now is that the atmospheric pressure, the container is so small, pretty much any container in real life satisfies this condition. The container is so small that there is really no difference in pressure between the top of the container and the orifice. So it's P atmospheric here as well as here. Okay. Therefore, this term does not matter anymore. Only this and this matter. Okay. And what is phi? Phi is simply, in this case, phi is simply something like gh, where g is a local acceleration due to gravity. Yeah, so you have phi minus gh. Let me write this again. Okay, so if you plug this in here, phi is minus gh, you can immediately see that you get half u squared is equal to gh, and therefore u squared is equal to, u out is equal to square root of 2gh. What did we do? We applied Bernoulli's constant to a particular streamline, to one streamline like this. Okay, so we invoked energy conservation along a particular streamline. This is what we did, and that immediately gives you this familiar result. Okay, let's go to another nifty result, and that is this. This is flow over an airfoil or essentially an aeroplane wing. Why does an aeroplane wing experience a lift? Okay, this is the fundamental principle around which aeroplanes are designed, and this is a rather simplistic way of explaining. If you really want to explain it properly, you have to take resort to what's called Kutta-Joukowski theorem, but we won't bother about those details at the minute. And it turns out that we can invoke the Bernoulli constant to show this. Okay, right. So turns out that now this figure does not emphasize this enough. So I will go to this. I will draw an airfoil, it really this is really how an airfoil looks. It's exaggerated, of course. The main thing is it's curved a little more here than here. Okay, it's curved a little more. And the Bernoulli constant, recall, the Bernoulli constant is half u squared plus p over rho plus phi. Okay, this is constant. So you write this down. Okay, so consider a streamline that's enveloping this kind of a circulation. Okay, now what happens is, because the airfoil is designed this way, okay, it turns out that the flow flows faster over. It's designed in a way that I should probably erase this. It's designed in a way, the velocity here is slower than the velocity out there. Okay, so the u here, I will draw this with a smaller arrow, and the u here, I'll draw this with a larger arrow. Okay, you can intuitively think of it like the palm of your hand, and velocity and fluid flowing like this. You can intuitively understand that the curvature, the cusp is such that it slows down fluid at the bottom as opposed to the top. Okay, as a result, in order and the phi is pretty much the same, as in this is a very thin airfoil. There's no difference in phi between here and here. The gravitational potential is pretty much the same. So we can essentially throw this away. We don't have to worry about this. Okay, now the u below is smaller than the u above, right? So and in order for this to be constant, because you're considering one streamline that's going around like this, therefore P below has to be greater than P above, right? And there you have it. Because P below is larger than P above, the airfoil experiences a lift. Okay, so this is how airplanes are able to fly. This is how the wing of an airplane experiences a lift, simply because it's designed in such a manner that you force the air to flow. It's cupped like this, and therefore the air at the bottom flows a little slower than the air at the top, and therefore, because if you consider one streamline, all throughout, and the Bernoulli constant is constant all throughout the streamline, you're making many assumptions here, of course, that the flow is inviscid and so on and so forth, not necessarily true in real world situations. In particular, you're neglecting effects like the boundary layer and things like this. But nonetheless, it's a very useful thing it's a very useful rough way of understanding this thing. Yeah. So because the velocity above is larger than the velocity below, the pressure, in order for the Bernoulli constant to be constant, the pressure above is smaller than the pressure below. In other words, there's a lift. The gradient in pressure gives you a force. Remember, force goes as gradient of pressure. And which direction is that force in? The force is in the upward direction. Yeah. So this is another neat illustration of the utility of the Bernoulli constant. And the next thing we will talk about is the vorticity equation, and maybe I'll very quickly go through it, and we will make a stop. So what you really do in talking about vorticity, recall, is this quantity, is the vorticity. This is what the vorticity is defined as. You start with the Euler equation and you take the curl of everything. Okay, so what you do is you do a d over you, and you assume that the space and time derivatives can be interchanged. So you do a d over dt curl of u. That's how you do this, and you take the curl of this. You take the curl of this. Yeah. So you curl everything. and you use this identity, same thing as what we encountered earlier while discussing the Bernoulli equation, and you write it as this, yeah, and you take the curl of the whole equation to get the time evolution of this quantity, which is the vorticity, and you end up with this equation, which we will discuss a little further, and we in particular we will specialize to what are called barotropic fluids, where the pressure is simply a function of the density. You've already encountered these things before. P equals nkt, for instance. Yeah, many fluids in real life are barotropic, and in doing so, we will get an evolution equation for this quantity called the vorticity, and that has very nice applications. It's a dynamical equation for the conservation of for the evolution of vorticity, and we will use that equation to derive to illustrate some other real life examples, such as the lift on a spinning ball. This is something that people who play tennis topspin are familiar with. We will discuss this when we come to it. And in order to understand that, we need to understand vorticity and the evolution of vorticity. So as we said, we are interested in getting an evolution equation for the vorticity. How the vorticity omega evolves as a function of time. Okay, and there will be, so the left hand side has time derivatives, the right hand side is going to have space derivatives. Okay, and the way we proceed is essentially you take the curl of this entire equation here, this entire equation, right? So we specialize to barotropic fluids, where the pressure is simply a function of the density. So if the pressure is a scalar function of the density, and this is something that you're familiar with, obviously, P equals nkt or rho kt, for instance. If this is the case, then the gradient of the pressure, you see you have a situation where you have a gradient of the density cross the gradient of the pressure. If the pressure is simply a function of density, then these two vectors are parallel to each other and the cross product vanishes, right? So you have a much simpler equation comprising of just these two terms, and yeah, so there you go. So this is a dynamical equation for vorticity. Okay, you might wonder, omega is the curl of u, okay, and you have u itself here. So if it's really a dynamical equation, not exclusively in terms of vorticity, but all in terms of, say, the uncurl of the vorticity, which is the velocity itself. But that's okay. It's still a dynamical equation for the vorticity. Yeah. So in principle, since omega is, that's what I just said, since omega is curl of u, right? Specifying both the curl and divergence of a vector field specifies the entire vector field uniquely. Okay. There are some caveats. The field has to be well behaved. In other words, you either at infinity you assume that the field dies away smoothly. You have to make that assumption, or you have to make sure that if you are imposing a boundary, the boundary conditions are well behaved. So this is simply by way of amplifying on the statement that specifying both the curl and divergence. So the curl is the vorticity, and we are talking about an incompressible fluid. In other words, divergence of u equals 0 is always satisfied. And of course, we are also talking about barotropic fluids, which is how we were able to throw away this last term. Right? We were able to throw away this last term because we were talking about barotropic fluids. But the point is, you are looking for an evolution of the curl, and you're looking at a situation where the divergence of u is 0. So you're in effect specifying both the curl and the divergence, and so it specifies the entire velocity field uniquely, with some caveats about the well-behaved nature of u at infinity, or if you're specifying a boundary, you have to specify the boundaries properly. But essentially, this is a full dynamical equation for the vorticity, or equivalently the velocity fields. Okay, so we will use this dynamical equation to define something called a circulation, and show that for an inviscid barotropic fluid, the circulation is a quantity called called this. It's a line integral of the fluid over, it's a closed line integral, and this is something that's conserved. And the conservation of circulation will enable us to derive some nifty results that we talked about. So we will do this when we meet next.